Hello, and welcome to Space for Sleep. When the first Apollo astronauts opened the hatch of the lunar module and looked down at the moon beneath their boots, they were not stepping onto a place that science already understood. They were stepping onto a world that had been watched for thousands of years and examined through telescopes for centuries, yet had never been touched, sampled, drilled, or listened to from the surface. From Earth, the moon seemed familiar. Its dark plains had names. Its mountains and craters had been mapped. Astronomers knew that it had almost no atmosphere, that its days and nights were long, and that its surface carried the scars of countless impacts. Robotic spacecraft had photographed it, crashed into it, and landed on it. But there was still an enormous difference between seeing a landscape from far away and knowing what it was made of. The central scientific question of Apollo was therefore simple to state and difficult to answer. What was the moon actually like? Was the gray surface a thin layer of dust covering solid rock, or a deep powder capable of swallowing a spacecraft? Were the dark lunar seas truly volcanic plains, as many geologists suspected, or were they something stranger? Were the bright highlands made from ancient crust, younger volcanic material, or debris thrown across the moon by enormous impacts? Was the moon cold and dead all the way through, or did it still move, crack, and release heat? Had it formed beside Earth, been captured by Earth, or separated from Earth in some violent event? And could its rocks preserve a record of the early solar system that Earth had lost? Between July 1969 and December 1972, 12 astronauts walked on the moon during 6 landing missions. They spent a combined total of almost 300 hours on the lunar surface. They drove electric rovers through valleys and across cratered plains. They photographed rock layers, hammered tubes into the soil, drilled into the ground, placed instruments, collected boulders, and filled sample bags with dust. They returned 2,196 documented samples, together weighing about 382 kilograms. Those numbers matter, but they do not capture what made Apollo scientifically powerful. The astronauts did not return an anonymous pile of moon rock. They returned samples whose locations, surroundings, depths, orientations, and relationships had been observed and recorded. A rock collected beside a crater rim meant something different from a similar rock lying on an undisturbed plain. A core taken from beneath the surface preserved a sequence of events. A glass bead mixed with orange soil could be linked to a particular landscape and a particular volcanic deposit. Context turned material into history. The astronauts also left part of the scientific expedition behind. Seismometers listened for moonquakes and impacts. Heat flow probes measured energy leaking from the interior. Magnetometers studied local magnetic fields. Detectors counted charged particles. Laser reflectors provided a target that observatories on Earth still use to measure the moon's motion with extraordinary precision. Apollo did not reveal a simple, lifeless stone. It revealed a differentiated world with a crust, mantle, and small metallic core. It revealed a moon that had once been largely molten, that had produced vast volcanic eruptions, that had possessed an ancient magnetic field, and that still experiences quakes. It revealed a surface continually changed by impacts, solar radiation, and microscopic particles traveling through space. It revealed traces of water in places where the first generation of analyses had seen only dryness. Most importantly, it revealed that the moon is an archive. Earth is active. Oceans move sediment. Wind erodes mountains. Rivers carry rock toward the sea. Volcanoes build new land. Plate tectonics pulls old crust into the mantle and creates new crust in its place. Life alters the atmosphere, soil, and chemistry of the surface. These processes make Earth habitable, but they also erase much of its earliest history. The moon has no oceans, no weather, no plate tectonics, and no global cycle that continuously replaces its crust. Its surface is not unchanged, but the changes are slower and different. Impacts break, melt, bury, and mix the rocks. Solar wind alters exposed grains. Dust migrates and settles. Yet pieces of crust more than 4 billion years old can remain available near the surface. Events that vanished from Earth can still be read in lunar stone. This is what the Apollo astronauts actually found. Not merely a destination, but a record of beginnings. Before anyone landed, the moon had already inspired several competing stories about its origin. One possibility was that Earth and Moon had formed together from the same cloud of material, growing side by side in the early solar system. Another was that the Moon had formed elsewhere and later been captured by Earth's gravity. A third older idea suggested that the young Earth had spun so rapidly that a portion of it separated and became the Moon. Each explanation had serious problems. Capture required an efficient way to remove energy from a passing body so that it would settle into orbit instead of escaping again. Formation together did not easily explain why the Moon has a much smaller metallic core and a lower overall density than Earth. Separation from a rapidly spinning Earth struggled to satisfy the physics of angular momentum. Before Apollo, there was no widely accepted answer. The Moon's surface history was equally uncertain. The dark regions called Maria, meaning seas, were widely interpreted as basaltic lava plains, but no one had held a piece of them. The brighter highlands looked older because they carried many more craters, but their composition was unknown. Some scientists expected dust tens of meters deep. Others argued that repeated impacts would compact the surface enough to support a lander. Engineers had to design for uncertainty because a mistake about the soil could destroy a mission. Robotic precursors reduced some of the danger. The Soviet Luna 9 spacecraft made the first successful soft landing in 1966 and showed that the surface could support a vehicle. American surveyor landers tested the mechanical properties of lunar soil and transmitted close views of the ground. Lunar orbiter spacecraft mapped possible landing sites. Still, small robotic feet and television cameras could not answer the deeper geological questions. Apollo 11 was designed first to prove that people could land and return safely. Its scientific program was deliberately limited by time, risk, and carrying capacity. Yet the first landing transformed lunar science almost immediately. Neil Armstrong and Buzz Aldrin spent about 2.5 hours outside the lunar module Eagle. Their working area was small. They remained close to the spacecraft, moved carefully, and followed a tightly planned sequence. Armstrong collected a small contingency sample soon after stepping onto the surface. If an emergency had forced the astronauts to leave almost immediately, at least a little lunar material would have returned with them. That simple act expressed the scientific priority clearly. Reaching the moon mattered. Bringing part of it home mattered too. The ground at Tranquility Base was firm beneath a shallow layer of loose material. Boots sank slightly, usually by only a few centimeters, though deeper patches existed. The soil could hold sharp impressions. The famous boot prints were not pressed into wet mud, and no moisture helped them keep their shape. Lunar grains are angular, irregular, and often jagged because they have not been rounded by flowing water or wind. Under pressure, they interlock, allowing the soil to preserve fine detail. The astronauts quickly learned that this material behaved in ways that were familiar and unfamiliar at once. It could be kicked, scooped, poured, and packed. In the moon's weak gravity, particles followed long, clean arcs. With no air, there was no billowing cloud in the earthly sense. Dust thrown by a boot or engine traveled on ballistic paths and fell back without being slowed by wind resistance. Yet the dust clung stubbornly to spacesuits, tools, camera equipment, and the lunar module. Electrostatic charging contributed to its behavior, but physical shape and mechanical embedding were also important. The grains worked into fabric and joints. They scratched surfaces and darkened the white suits. The problem became more serious on later missions, when crews spent longer outside and drove vehicles that threw dust across equipment. Inside the cabin, astronauts noticed a distinctive smell after dusty suits and sample containers were brought in. Several compared it to spent gunpowder or wet ashes. Lunar soil had not burned. The comparison described a sensation produced when fresh, chemically reactive grain surfaces encountered oxygen and moisture inside the spacecraft. On the Moon, those surfaces had been created by impacts and remained exposed to vacuum. In the cabin, they entered an environment unlike any they had experienced before. The Apollo crews also reported irritation of the eyes, nose, or throat after dust entered the cabin. Their exposures were brief, and the long-term health effects remain uncertain, but the lesson was clear. The lunar surface was not a soft, harmless powder. It was an abrasive material capable of damaging seals, fabrics, mechanisms, and perhaps lungs. This practical discovery was also a geological one. Lunar soil, usually called regolith when referring to the entire loose layer, is produced over immense periods by impacts. Large impacts excavate craters and throw blocks across the surface. Small impacts shatter rock. Micrometeorites strike at high speed, melting tiny portions of soil and rock. The melted material cools into glass or welds grains together into irregular particles called agglutinates. Solar wind implants hydrogen, helium, and other ions into exposed grains. Cosmic rays leave tracks inside minerals. A handful of lunar soil, therefore, contains fragments of many histories. It may include pieces of local bedrock, debris from distant impacts, volcanic glass, impact glass, meteoritic material, and grains altered by exposure to space. Soil is not merely crushed rock. It is a record of the environment at an airless surface. Armstrong and Aldrin collected dark basaltic rocks, lighter fragments, and soil from the Sea of Tranquility. When the samples reached laboratories on Earth, scientists found that the dark plains were indeed volcanic. The rocks were basalts, formed when molten material rose from inside the Moon, spread across low regions, and cooled. The confirmation may sound unsurprising now, but it changed the status of the Moon. The Maria were no longer only dark markings interpreted from photographs. They were ancient lava plains with measurable mineral compositions and ages. Many Apollo 11 basalts formed roughly 3.5 to nearly 4 billion years ago. They contained minerals familiar from terrestrial volcanic rocks, including pyroxene, plagioclase, and ilmenite, but in combinations shaped by the Moon's different chemistry and environment. They showed that the Moon had once been hot enough inside to produce large volumes of magma long after its primary crust had formed. They also contained almost no evidence of the chemical alteration that water produces so commonly on Earth. No rain had passed through them. No ocean had changed them. No soil organisms had worked on their surfaces. Their minerals preserved an exceptionally direct record of crystallization. The first samples demonstrated that the Moon was ancient, but they also warned scientists against treating any single landing site as representative of the entire world. Tranquility Base lay on a mere plain. Its rocks told the story of volcanism and impacts in one region. To reconstruct the Moon, Apollo would have to visit different landscapes. The soil carried another message from beyond the Moon. Aldrin deployed a simple sheet of aluminium foil facing the sun. For a little more than an hour, particles in the solar wind struck the foil and became embedded in it. He then rolled it up and returned it to Earth. The experiment looked almost too simple for spaceflight. It had no motor, computer, or radio transmitter. But in laboratories, researchers extracted helium, neon, argon, and other particles captured from the solar wind. The foil provided a direct sample of material flowing from the sun. Later Apollo missions repeated the experiment for longer periods. The results helped scientists study solar composition and the processes that fractionate elements as they travel outward. The moon's lack of a thick atmosphere and global magnetic field made its surface an exposed collector. Every grain of mature regolith had been receiving the solar wind for ages. Apollo brought some of that implanted solar history back to Earth. Nearby, the astronauts placed a laser retroreflector. Its array of corner cube reflectors was designed to return incoming light toward its source. Observatories on Earth could fire short laser pulses toward the landing site and detect a tiny fraction of the photons returning from the moon. The first successful measurements were not accurate to the millimeter. Decades of improved lasers, detectors, timing systems, atmospheric models, and observatory networks gradually increased the precision. The reflector itself needed no power. It simply remained on the surface, waiting for light. These measurements would eventually reveal that the moon is moving away from Earth by about 3.8 centimeters per year. They would test the way Earth and moon fall toward the sun, constrain theories of gravity, track subtle changes in the moon's rotation, and provide clues to its interior. An object placed during the first landing became one of Apollo's longest scientific conversations with the moon. Apollo 11 also carried a passive seismometer. Its useful operation was brief compared with the stations deployed later, but it began the attempt to listen to the moon. The instrument detected vibrations from astronaut activity, the lunar module, and the surface environment. More capable stations would soon form a small seismic network. The moon looked motionless. Seismology would show that it was not. The first landing therefore found several different moons at once. It found a volcanic moon in the basalt. It found an impact-processed moon in the soil. It found a body exposed directly to the sun in the implanted particles. It found a world whose distance and motion could be measured with reflected light. And it found a surface difficult enough to challenge every future suit, tool, and machine. But Apollo 11 had sampled only one plane, close to one lander, during one short excursion. The scientific expedition was just beginning. Apollo 12 returned 4 months later with a different purpose. The first mission had demonstrated that a landing was possible. The second would demonstrate precision. Pete Conrad and Alan Bean landed the lunar module Intrepid in the Ocean of Storms, only about 155 meters from Surveyor 3, a robotic spacecraft that had arrived 2.5 years earlier. The ability to land within walking distance of a small target changed the future of lunar exploration. It meant that later crews could aim for scientifically chosen features rather than broad, forgiving zones. Surveyor 3 offered an experiment no one could have performed before. A machine built on Earth had remained on the moon through repeated cycles of extreme heat and cold, exposure to radiation, vacuum, micrometeorites, and dust. Conrad and Bean photographed it, cut away its television camera and other components, and returned them for analysis. The retrieved hardware showed pitting, dust effects, and material changes. It also became part of a famous lesson in contamination. A bacterium was reported from a piece of foam associated with the returned camera, leading to claims that terrestrial microbes had survived for years on the moon. Later reviews of the handling history showed that contamination before launch or during recovery and laboratory analysis could explain the result far better than years of survival on the lunar surface. The episode became a warning about how easily biological conclusions can be distorted when sample control is imperfect. That warning remains important for every mission searching for life or returning material from another world. Extraordinary biological claims require not only a detected organism or molecule, but an unbroken understanding of how the sample was collected, sealed, transported, and analyzed. The Apollo 12 landing site also let scientists compare two mare regions. The basalts differed from those returned by Apollo 11. Some were younger, with ages around 3.2 billion years. Their chemistry showed that lunar volcanism was not a single global event. Different regions had melted at different times and produced magmas from different parts of the mantle. This was the beginning of a more complicated volcanic history. The moon had not simply formed, cooled, and become inactive. It had produced lava across a long interval. The dark Maria represented many eruptions and flows, filling impact basins and stages. Conrad and Bean deployed the first full Apollo lunar surface experiments package. Its nuclear power source allowed instruments to survive the 2-week lunar night, when solar-powered equipment faced prolonged darkness and extreme cold. The package included a more capable seismometer, a magnetometer, a solar wind spectrometer, and other experiments. The surface station continued working after the astronauts departed. The landing site became an observatory. One of the most useful seismic signals was created deliberately. After the astronauts returned to orbit, the ascent stage of the lunar module was guided into the moon. Its mass and impact speed were known. Scientists could compare the resulting vibrations with a controlled source, rather like striking an unknown object and listening to how it responded. The signal lasted far longer than an equivalent impact vibration on Earth. The moon reverberated. The popular phrase says that it rang like a bell. A better comparison is sometimes a gong. Earth's warm, fractured, fluid-influenced interior absorbs and scatters seismic energy in ways that damp many vibrations relatively quickly. The cold, dry, highly fractured upper moon scattered waves repeatedly while absorbing them slowly. Signals continued through overlapping paths, producing a long, complex decay. This was not evidence that the moon was hollow. It was evidence that its interior and crust were physically different from Earth's. Apollo 12 also collected soil and rocks crossed by rays from the relatively young crater Copernicus, though connecting individual samples to distant source events proved difficult. The landing showed both the promise and challenge of lunar geology. Impacts can transport material hundreds of kilometers, mixing local and distant histories. A geologist on the moon may stand in one place while holding fragments from many places and times. The astronauts had now visited 2 volcanic plains. The next goal was to reach material connected with one of the moon's enormous impact basins and learn how catastrophic collisions had reshaped the crust. Apollo 13 was assigned to the Fra Mauro formation, but the explosion in its service module prevented a landing. The crew returned safely, and the scientific destination passed to Apollo 14. At Fra Mauro, the story of the moon would begin to move from lava plains toward impacts large enough to alter an entire world. Alan Shepard and Edgar Mitchell landed at Fra Mauro in February 1971. The landscape did not announce its history with a dramatic cliff or exposed wall. It looked like rolling, dusty terrain scattered with craters and rocks. Yet much of the material beneath their boots was believed to have been thrown outward by the impact that formed the Imbrium Basin, one of the largest and most prominent structures on the near side of the moon. The scale of such an event is difficult to picture from the ground. Mare Imbrium is more than 1,000 kilometers across. Its formation excavated and melted immense volumes of crust. Debris traveled outward in sheets, burying older terrain. Later lava flooded parts of the basin, creating the dark plain visible from Earth. Fra Mauro lay beyond the mare, in deposits interpreted as ejecta from that basin forming impact. If the interpretation was correct, rocks there could help determine when Imbrium formed and reveal material excavated from deep in the lunar crust. Shepard and Mitchell's major geological traverse led toward Cone Crater. The crater was much smaller than Imbrium, but scientifically useful because its impact had dug through the local surface and brought buried material upward. A young crater can act like a natural drill. Its deepest ejecta are often found near the rim, where astronauts could collect them without descending into the crater. The route was more difficult than expected. The crew pulled a two-wheeled equipment cart through rolling terrain while wearing stiff suits with limited visibility. Landmarks were hard to recognize. Distances were deceptive in the airless landscape, where there was no haze to soften distant features and few familiar objects to provide scale. They climbed, sampled, described, and continued upward, believing the rim still lay ahead. In fact, they came within a few tens of meters of it before time and oxygen constraints forced them to turn back. They never saw into Cone Crater. It might sound like a failed geological traverse. It was not. The crew reached the ejecta field near the rim and collected material that had been excavated from depth. Their samples included breccias, rocks composed of fragments broken and welded together by impacts. One large specimen, informally called Big Bertha, weighed almost 9 kilograms. Breccias became central to understanding the moon. On Earth, a geologist often studies rocks formed by cooling magma, accumulating sediment, or changing under heat and pressure. On the moon, impact breccias are everywhere. They contain pieces of older rocks assembled during violent events. Some were simply crushed and compacted. Others were partly or completely melted before cooling again. A single breccia can preserve minerals and fragments from several episodes separated by hundreds of millions of years. This makes them difficult and valuable. Their mixed nature can confuse a simple age measurement, but careful analysis can separate components and reconstruct events. Apollo scientists learned that impact geology was not a minor surface process. It was one of the main forces that built the landscapes of the early inner solar system. The Fra Mauro samples helped tie many impact melt ages to the period around 3.9 billion years ago, close to the estimated age of the Imbrium Basin. Similar age clusters appeared in samples from other landing sites. This contributed to the idea of a late heavy bombardment, sometimes called the lunar cataclysm, a relatively brief interval when the impact rate in the inner solar system rose dramatically long after the planets had formed. For decades, this became one of Apollo's most influential interpretations. If the moon experienced a surge of giant impacts around 3.9 billion years ago, Earth would have experienced it too. The timing would overlap with the earliest evidence for life and with the period when Earth's oldest surviving crust was forming. The modern picture is less settled. Apollo landing sites are concentrated on the near side, and several are affected by debris from Imbrium. A cluster of measured ages can therefore overrepresent one enormous basin rather than record a solar system-wide spike. Lunar meteorites and newer analyses have broadened the sample set, while dynamical models offer several possible histories for the declining population of impactors. Some researchers still support a distinct episode of intense bombardment. Others favor a smoother decline interrupted by major impacts, or a prolonged interval rather than a narrow cataclysm. The samples establish that the early moon endured enormous collisions. They do not yet provide a perfectly complete timetable for every basin. This uncertainty is part of the scientific legacy, not a failure of it. Apollo gave researchers enough evidence to discover a major question, but not enough geographic coverage to close it. The exact early impact history remains one of the reasons scientists want samples from places far from the Apollo sites, especially from the enormous South Pole Aitken Basin on the far side. The Fra Mauro rocks also contained a chemical signature that became famous in lunar science. Some samples were enriched in potassium, rare earth elements, and phosphorus. The acronym formed from these elements is KREP. KREP is not a single mineral. It represents material enriched in elements that do not fit easily into the common minerals crystallizing from magma. As the ancient lunar magma ocean cooled, minerals such as olivine, pyroxene, and plagioclase formed and separated. Many incompatible elements remained concentrated in the last portions of melt. That residual material carried uranium, thorium, potassium, and other heat-producing or geochemically distinctive elements. Much of the near side contains evidence of this enriched material, especially around the region called the Procellarum KREP terrain. The concentration of radioactive elements may have helped sustain volcanism there longer than in other parts of the Moon. Apollo samples therefore hinted that the lunar interior was not chemically uniform. Different regions carried different thermal and compositional histories. Apollo 14 also deployed scientific instruments and performed an active seismic experiment. Small explosive charges and a mechanical thumper created known vibrations. By measuring how the waves traveled through shallow layers, scientists could estimate the structure and thickness of the local regolith. The experiment brought geology into the realm of soundless motion. No human ear could hear the waves in the vacuum, but instruments felt them pass through the ground. Beneath the loose surface lay layers produced by repeated impacts, burial, and excavation. By the time Shepard and Mitchell left, Apollo had sampled 2 mare plains and 1 major basin ejected deposit. The next mission would go somewhere more ambitious, a boundary between a dark volcanic sea and one of the Moon's great mountain ranges. Apollo 15 marked a change in the program. The early missions had been constrained by the need to prove each step safely. Apollo 15 was designed as a longer scientific expedition. David Scott and James Irwin had a lunar rover, improved life support capacity, more time outside, and a landing site chosen for geological variety. Hadley Apennine lay beside the eastern edge of Mare Imbrium. The lunar module Falcon descended near the base of mountains rising several kilometers above the plain. Nearby, Hadley Rill curved across the landscape like a dry river channel. It was not carved by water. It was a volcanic feature. Sinuous rills are generally interpreted as channels or collapsed lava tubes formed when low-viscosity lava flowed across the Moon. Hadley Rill is more than 1 kilometer wide in places and hundreds of meters deep. Its walls expose layers that are otherwise hidden beneath the Mare's surface. From orbit, the feature looked dramatic. From the ground, its far wall and layered outcrops offered a direct view into the volcanic history of the plain. Scott and Irwin drove to its edge, photographed the walls, and collected rocks from nearby craters and ejecta. The rover changed the scale of fieldwork. Instead of remaining within a small walking radius, the astronauts traveled kilometers from the lunar module. They could stop at selected stations, collect samples, describe boulders, and carry much more material than a person could transport by hand. Driving on the Moon was not smooth. The rover bounced in the weak gravity. Its wheels threw rooster tails of dust that followed clean parabolic arcs. Navigation depended on heading, distance, maps, landmarks, and judgment. There was no road, no magnetic compass useful in the ordinary way, and no rescue vehicle waiting beyond the hills. The increased range made it possible to sample both Mare basalt and highland material. It also produced the most famous rock collected by Apollo 15. At Spur Crater, Scott noticed a light-colored rock standing out against darker material. He and Irwin had trained to recognize anorthosite, the rock expected to make up much of the ancient lunar highland crust. Their excitement was audible as they examined the sample. The rock, numbered 15,415 and nicknamed the Genesis Rock, was rich in plagioclase feldspar. It was not the oldest lunar material ever found, and it was not an untouched piece from the first instant of lunar history. It had experienced later events, but it was a fragment of ancient anorthositic crust, roughly 4 billion years old, and it supported one of Apollo's most important ideas. The young Moon had once possessed a global or near-global magma ocean. Soon after the Moon formed, enormous amounts of energy kept much of its outer region molten. Impacts during accretion released heat. Radioactive elements decayed. If the moon formed from a giant debris disk, the assembly process itself was energetic. The result was not a cold ball of rock, but a world covered, at least to considerable depth, by molten silicate. As that magma cooled, minerals crystallized. Dense minerals tended to sink. Plagioclase feldspar was less dense than the surrounding melt and tended to rise. Accumulations of plagioclase formed a buoyant primary crust dominated by anorthosite. This process explained the bright highlands. They were not merely old volcanic mountains. They were remnants of the moon's early differentiated crust, later shattered and rearranged by impacts. Apollo 11 had found dark basalt from later volcanic plains. Apollo 15 found pale material connected to the older crust beneath and around those plains. Together, the samples revealed sequence: formation, melting, differentiation, crust building, impacts, and later volcanism. The moon had a geological biography. Apollo 15 also returned tiny green glass beads. Like the orange glass later found by Apollo 17, they formed during explosive volcanic eruptions. Gas escaping from rising magma drove fountains of molten droplets above the surface. In vacuum and weak gravity, the droplets followed arcs, cooled, and fell as glassy beads. The existence of fire fountain deposits challenged the image of lunar volcanism as only quiet sheets of lava. The moon had experienced explosive eruptions, though not explosions produced by expanding atmospheric steam in the terrestrial sense. Volatile compounds dissolved in magma could separate into gas as pressure fell, driving jets and fountains into vacuum. Decades later, improved instruments would detect hydrogen and other volatile signatures within these beads. A sample small enough to sit on a fingertip would overturn the idea that the moon's interior had always been almost perfectly dry. Another Apollo 15 sample, a mare basalt often called the seatbelt basalt because Scott collected it during an unscheduled stop, illustrated the advantage of human flexibility. Mission planners wanted the crew to return, and time was limited. Scott recognized a useful rock, paused briefly, and picked it up without a long, formal sampling sequence. Its later study contributed to the volcanic record of the site. The moment has sometimes been described as secretive, but scientifically it represents a field geologist's instinct operating under rigid mission rules. A robot executes instructions. A trained person can notice that an ordinary-looking stone may answer a question and make a decision in seconds. The Apollo 15 crew also drilled a deep core. Core tubes preserve vertical order. The material at the top has been exposed most recently. Deeper layers may record older surfaces buried by ejecta or gradual mixing. Cosmic ray tracks, implanted solar particles, glass layers, and changes in grain maturity can provide clues to how long material remained exposed and how often it was overturned. The lunar surface is slowly churned by impacts in a process called impact gardening. A micrometeorite may disturb a tiny patch. A larger crater may bury a wide region beneath ejecta. Over millions and billions of years, the upper regolith is mixed, but not perfectly. Cores preserve partial sequences through this changing layer. Apollo 15's scientific station included a heat flow experiment. Scott drilled holes and inserted probes to measure temperature below the surface. The aim was to determine how much heat was moving outward from the moon's interior. Drilling proved unexpectedly difficult. The regolith became denser with depth, and the drill stem resisted extraction. The challenge itself supplied information about the mechanical behavior of the ground. Lunar soil was not a uniform powder. It changed as overlying material compacted it, and as impact history altered the subsurface. Heat flow measurements from Apollo 15 and later Apollo 17 indicated that the moon still loses internal heat. Some energy is primordial, left from formation and differentiation. Some is generated by radioactive decay. The measured values were lower than typical terrestrial continental heat flow, consistent with a smaller body that had cooled more extensively. But there was a complication. Both successful heat flow sites were in or near geochemically unusual regions enriched in heat-producing elements. They may not represent the global average. The experiment answered one question and exposed another. How different is heat flow across the moon? A second complication emerged decades later when old data were recovered and reanalyzed. Temperatures near the surface had gradually increased after the astronauts arrived. Images of the landing sites suggested that astronaut activity had disturbed and darkened the soil, allowing it to absorb more sunlight. Human footprints and operations had subtly changed the thermal environment the instruments were trying to measure. The effect was strongest near the surface and did not erase the deeper heat flow result. Still, it provided a beautiful example of experimental humility. Even on the moon, an observer can alter the system being observed. Apollo 15 also placed another laser reflector and additional instruments. In lunar orbit, the command module carried cameras, an X-ray fluorescence experiment, gamma-ray measurements, and a small subsatellite. Apollo science was no longer limited to the ground directly beneath the astronauts. Surface observations, orbital mapping, and laboratory analysis were being combined into one investigation. When Scott and Irwin left Hadley Apennine, they had shown what a mobile human expedition could do. They had visited a volcanic channel, sampled mare and highland material, drilled into the regolith, and collected evidence of ancient crust and explosive volcanism. The next mission would test geological interpretation more sharply. Apollo 16 was sent to the Descartes Highlands, the only Apollo landing site entirely within the bright, ancient terrain away from direct mare sampling. From orbital photographs, 2 units called the Cayley Plains and Descartes Formation had been interpreted by many scientists as volcanic. Their smooth or hilly appearances seemed consistent with lavas or other internally produced deposits. John Young and Charles Duke were expected to collect rocks from a kind of lunar volcanism different from mare basalt. They found almost none. The landing site was dominated by breccias and impact-related material. The plains and hills that had looked volcanic from orbit had been built or heavily reworked by impacts. The Cayley material was largely ejecta, much of it associated with basin-forming events, rather than a separate volcanic province. This was one of Apollo's clearest scientific surprises. A reasonable interpretation based on remote images had failed when tested by samples on the ground. The lesson extended beyond the moon. Planetary scientists study worlds mainly through images, spectra, gravity measurements, and other remote data. Landforms can resemble one another while having different origins. A smooth plain may be lava, sediment, impact melt, or ejecta. Ground truth is the evidence that forces interpretation to match material reality. Apollo 16 provided ground truth for the lunar highlands. Young and Duke found anorthositic fragments, impact melts, and complex breccias representing a crust that had been shattered repeatedly. Some breccias contained clasts from older rocks embedded in younger impact-produced matrices. Others recorded high temperatures and pressures. Their textures preserved collisions at scales ranging from local craters to giant basins. The astronauts also encountered large boulders and sampled rays extending from South Ray Crater. Fresh craters exposed less weathered material, allowing comparisons with older soil that had spent longer at the surface. Bright rays fade over time as space weathering darkens and reddens exposed grains, and as impacts mix ejecta into surrounding regolith. Space weathering is slow transformation without air or rain. Micrometeorite impacts melt grain surfaces. Solar wind implants ions. Nanometer-scale metallic iron forms in glassy coatings and agglutinates. These changes alter how the surface reflects light. The color of a lunar landscape is therefore not determined only by its original rock. Exposure age matters. Fresh crater material can look bright even when its composition resembles darker surroundings. Apollo samples helped scientists connect microscopic alteration to the broad patterns seen through telescopes. Apollo 16's active seismic experiment used small explosive charges placed at varying distances from the station. After the astronauts departed, commands from Earth detonated some charges, creating controlled seismic sources. Combined with signals from a mortar system and other impacts, the data revealed shallow layering beneath the site. The mission also carried a far ultraviolet camera and spectrograph, the first astronomical observatory operated by humans on another world. Placed in the shadow of the lunar module, it photographed Earth's outer atmosphere, stars, nebulae, and other targets in wavelengths blocked by Earth's atmosphere. The moon became not only an object of study, but a platform for studying the universe. Apollo 16 overturned the expected volcanic story of Descartes, strengthened the evidence that impacts dominate highland geology, and showed why returned samples are indispensable. Yet the program still lacked a professional geologist on the surface. The final landing would change that. Apollo 17 landed in the Taurus Littrow Valley in December 1972. Gene Cernan commanded the mission. Harrison Schmitt, a trained geologist, served as lunar module pilot. Ronald Evans remained in lunar orbit, operating an extensive suite of instruments while his crewmates explored below. Taurus Littrow was selected because it brought several geological possibilities together. The valley lay among ancient highland massifs at the edge of the Serenitatis Basin. Its floor contained dark deposits and mare material. Large boulders had rolled down mountain slopes, potentially carrying samples from high above. Orbital observations had suggested that some deposits might be young volcanic material. The mission was designed to ask questions across the moon's history. How old were the mountain materials? What produced the dark mantle? Had volcanic activity continued until relatively recent times? Could a geologist recognize relationships on the surface that photographs alone could not resolve? Cernan and Schmitt spent more than 3 days on the moon and performed 3 long excursions. Their rover carried them across the valley floor to crater rims, boulder fields, and the bases of mountains. They returned about 110 kilograms of material, more than any other Apollo landing. Schmidt's professional background did not turn every glance into a discovery. Field geology is rarely so effortless. The surface was dusty, the timetable was strict, and many rocks were breccias whose histories could not be read completely through a helmet visor. But geological training shaped what he noticed, how he described it, and which relationships he considered important. At Station 6, near the base of the North Massif, the crew examined a large boulder that had rolled down the slope, leaving a track visible behind it. The boulder offered pieces from material exposed higher on the mountain. By sampling different portions and documenting its position, the astronauts could connect fragments to a larger geological setting. The scene illustrates why scale matters. A laboratory can reveal the chemistry and age of a gram of rock with extraordinary precision. It cannot show where that rock rested in relation to a slope, a crater, or a neighboring layer unless field observations preserve that information. The most famous discovery came at Shorty Crater. As the crew worked near the crater, Schmitt noticed that the soil beneath the usual gray surface had a vivid orange color. It was so unexpected that he first wondered whether the color could be caused by something on his visor. Cernan saw it too. They had found a deposit of tiny orange and black glass beads. The color looked almost biological by lunar standards, but the material was not evidence of life, rust produced by rain, or recent burning. Laboratory analysis showed that the beads were volcanic. They had formed roughly 3.5 billion years ago during explosive eruptions. Imagine magma rising from the lunar interior. Pressure decreases as it approaches the surface. Volatile compounds dissolved in the melt-form gas. With almost no atmosphere pressing down, the expanding gas can propel molten droplets into a fountain. The droplets cool during flight and fall back as glass. Some beads remained glassy and orange. Others crystallized and appeared dark. Their chemistry, including abundant titanium and iron in the Apollo 17 deposit, produced the unusual color. The discovery solved one question and complicated another. The dark mantle at Taurus Litrove was not evidence of very recent volcanism. The orange glass was ancient, broadly similar in age to much mere volcanism. The apparently youthful surface expression resulted from geological exposure and preservation, not a young eruption. Once again, appearance from orbit had suggested one story, while samples revealed another. The beads also carried volatile elements. Sulfur, fluorine, chlorine, zinc, and other substances were concentrated in coatings or within the volcanic products. These materials had traveled with erupting gas from inside the moon. At the time, however, the dominant interpretation of Apollo samples was that the moon was extremely dry. Many analyses found very little water, and the leading models of lunar formation involved temperatures high enough to remove volatile compounds efficiently. The orange and green glasses were known to be volcanic, but the full significance of their hydrogen content had to wait for better instruments. In 2008, researchers reanalyzed volcanic glass beads from Apollo samples using methods capable of examining tiny variations within individual particles. They detected hydrogen interpreted as evidence of water originally dissolved in lunar magma. The distribution was crucial. Some beads contained more hydrogen toward their centers and less near their edges. That pattern was consistent with water escaping as the molten droplet traveled through a volcanic eruption. It was not simply moisture added later from Earth. Further studies of volcanic glasses, melt inclusions trapped inside crystals, and other Apollo samples strengthened the conclusion. The moon's mantle was not uniformly bone dry. At least some source regions contained water and other volatiles. The amounts were small by terrestrial standards, and the findings did not mean that underground oceans existed inside the moon. They meant that the early assumption of almost total dryness was too simple. This discovery altered theories of lunar origin. A giant impact energetic enough to create the moon might be expected to drive away volatile elements. Yet some survived, were inherited, or were delivered and mixed in ways that models must explain. The water in Apollo glass became a constraint on the temperature, pressure, mixing, and cooling of the moon-forming event. It also changed how scientists thought about lunar volcanism. Gas played a real role. The fountains that created glass beads were powered by volatile release. A world without oceans or a thick atmosphere could still have an interior carrying ingredients associated with water. Apollo 17 collected more than orange soil. The mission returned basalts, breccias, ancient highland fragments, impact melts, cores, and soils with different exposure histories. Some basalts were around 3.7 billion years old. Highland materials recorded older events. The combination allowed scientists to compare the valley floor with surrounding mountains and basin history. One unusual pale material found around several locations was later interpreted as a deposit formed by an avalanche or landslide from the South Massif, possibly triggered by the impact that created Tycho crater far away. The exact relationships remain subjects of study, but the possibility demonstrates the reach of major impacts. An event hundreds or thousands of kilometers away can send seismic energy through the moon, destabilize slopes, and scatter ejecta across broad regions. The crew deployed a surface gravimeter intended to detect gravitational waves and study lunar tides. though the instrument did not work as originally designed. They also placed geophones and explosive charges for a lunar seismic profiling experiment. The charges were detonated after the astronauts left, allowing scientists to probe shallow structure across the valley. Not every Apollo experiment succeeded. Some instruments failed, behaved unexpectedly, or produced data more limited than planners hoped. The science did not depend on a perfect set of machines. It grew from the combined record of successful experiments, partial results, returned samples, photographs, transcripts, orbital observations, and later missions. Even mistakes and malfunctions taught engineers how difficult it is to operate precision equipment in vacuum, dust, extreme temperatures, and reduced gravity. Cernan and Schmidt also experienced the practical limits of the surface. Dust-coated equipment. Fenders on the rover mattered because a missing extension allowed dust to spray over the astronauts and vehicle. The crew improvised a replacement using maps, tape, and clamps. The repair reduced the problem. That improvised fender has a scientific lesson hidden inside it. Exploration is not only the collection of planned data. It is the maintenance of the conditions that make data collection possible. A dusty radiator may overheat. A contaminated camera may lose contrast. A jammed joint may shorten an excursion. The geology of the moon interacts directly with human systems. When Apollo 17 lifted off, the human exploration of the surface ended. But the instruments left by several missions continued transmitting until 1977, and the samples entered a much longer scientific life. The seismic network became one of the most important experiments. Seismology does not require a visible opening into a world. Waves passing through rock change speed, direction, and amplitude when they encounter different materials. By comparing arrival times at several stations, researchers can locate events and infer internal layers. The Apollo network was small and geographically limited. All stations stood on the near side within a relatively narrow region. Data quality was constrained by the instruments, timing, noise, and the complex scattering of waves in the lunar crust. Even so, the network recorded thousands of natural and artificial events. The events fell into several broad categories. Deep moonquakes occurred hundreds of kilometers below the surface, commonly around 700 to 1,200 kilometers deep. They repeated at particular source regions and followed tidal cycles. As the moon traveled around Earth, changing gravitational stresses flexed the interior. Certain zones slipped or cracked repeatedly under this periodic loading. Most deep moonquakes were weak. Their importance came from repetition and location. They showed that the deep moon responds to Earth's pull and is not perfectly rigid. Shallow moonquakes were rarer and potentially stronger. They originated tens of kilometers below the surface and did not follow the same simple tidal pattern. Some may be associated with long-term cooling and contraction, fault movement, or other tectonic stresses. Later orbital images revealed young thrust faults and scarps, supporting the idea that the moon has continued to shrink slightly as its interior loses heat. Thermal moonquakes occurred near the surface as rocks and regolith expanded and contracted through the enormous temperature change between lunar night and day. The sun rises slowly on the moon, but the thermal transition is severe. Material that has spent about 2 Earth weeks in darkness warms under sunlight, and mechanical stress produces small signals. Meteoroid impacts created another category. With no thick atmosphere to burn up small incoming bodies, the moon receives direct strikes. The seismic network recorded impacts, and deliberate crashes provided controlled events. Rocket stages and lunar module ascent stages hit at known times and locations, helping scientists calibrate wave travel. The long reverberation of signals revealed a dry, fractured upper region with low attenuation. Waves scattered through cracks and broken rock created long codas after the first arrival. The phrase that the moon rang like a bell captured the duration, though not the exact physics. By analyzing these waves, researchers developed the first internal models of another planetary body using seismology. The moon has a crust, mantle, and core. That may seem obvious now, but Apollo provided direct evidence for layering. The crust beneath the Apollo network was initially estimated to be thicker than modern global estimates. Later gravity data, improved processing, and reanalysis refined the picture. Average lunar crustal thickness is now thought to be on the order of several tens of kilometers, with major regional variations. Beneath the crust lies a mantle dominated by silicate rock. Seismic velocities change with depth and composition. At great depth, a partially molten or low-velocity region may exist near the core mantle boundary. At the center is a small metallic core, probably containing solid and liquid portions. Its exact dimensions and composition remain uncertain because the Apollo network had limited coverage and relatively few waves passed cleanly through the deepest interior. Laser ranging, magnetic studies, gravity data, and modern reanalysis have helped constrain it. The core occupies a much smaller fraction of the moon than Earth's core occupies of Earth. This small core fits a basic compositional difference. The moon contains less metallic iron relative to silicate than Earth as a whole. Any formation theory must explain why the two bodies are isotopically similar in many ways, but structurally different in metal content. The seismic data also showed why declaring the moon geologically dead is misleading. It has no active plate tectonics, no known present volcanic eruptions, and far less internal energy than Earth. But it moves. It cracks. It responds to tides. Its surface is struck continuously. Its crust carries stress. Dead and alive are biological words that do not map neatly onto planetary geology. The moon is active at a quiet scale. Apollo's heat flow experiments added another dimension to this internal picture. Probes at Apollo 15 and 17 measured temperature with depth and thermal conductivity. The resulting heat flow was modest but real. Radioactive elements such as uranium, thorium, and potassium produce heat as they decay. Their distribution matters. KREP-rich regions on the near side contain more of them than much of the rest of the crust. Because both successful Apollo heat flow measurements were made in geochemically unusual terrain, scientists cannot simply average the two values and declare a global answer. This geographic bias resembles the seismic limitation. Apollo produced priceless direct measurements, but all 6 landing sites occupied a relatively small portion of the near side at low to middle latitudes. The far side, polar regions, and many major geological provinces remained unsampled and uninstrumented. The data were both foundational and incomplete. Apollo magnetometers and magnetic measurements of returned rocks revealed another unexpected chapter. The moon today has no strong global dipole field like Earth's. A compass would not point reliably toward a lunar north magnetic pole. Yet many ancient rocks carried remnant magnetization, a record of magnetic fields present when they cooled or were altered. This indicated that the early moon once generated a magnetic field, probably through a dynamo in its liquid core. On Earth, motion in the electrically conducting outer core sustains the global magnetic field. The moon's smaller core and faster cooling make a long-lived dynamo more difficult to explain. Yet some Apollo rocks record strong ancient fields, and magnetization persisted in samples much younger than the earliest crust. Scientists have proposed several energy sources. Convection driven by cooling or chemical separation may have powered the dynamo. Mechanical stirring related to Earth's tidal influence or changes in the moon's rotation may have contributed during certain periods. Large impacts can also magnetize rocks locally or complicate the record. The timing and strength of the lunar dynamo remain active questions. Apollo did not give one simple answer. It revealed that the moon's interior had once been more dynamic than anyone looking at the silent modern surface might imagine. A rock carried home in a sample bag could therefore record an invisible field that vanished billions of years ago. This is one of the recurring patterns of Apollo science. The astronauts saw gray stones. Laboratories found time, temperature, pressure, magnetism, radiation exposure, and volatile loss preserved inside them. The same was true of the regolith. Mature lunar soil contains particles implanted by the solar wind. Helium, neon, argon, hydrogen, and other ions strike exposed grains directly. Over time, the upper surface becomes a record of the sun. The solar wind collector foils gave clean, short-duration samples. Soil offered a long, complicated archive. By comparing noble gases and isotopes, scientists could study solar composition and how exposure changed over geological time. The record is imperfect because impacts mix grains, and because implanted particles can be lost during heating. Yet it means that the moon preserves not only its own evolution, but aspects of the sun's behavior. Apollo went to one world and returned evidence about two. It also returned evidence about asteroids and comets. Meteorites striking the moon contribute small amounts of foreign material. Some impactors vaporize almost completely. Others leave chemical or isotopic traces in breccias and soils. Highly siderophile elements, which prefer metal, can reveal additions from impactors after the lunar crust formed. Untangling these contributions helps reconstruct the population of objects that moved through the early solar system. The moon has acted as a witness to bombardment that also affected Earth, but whose terrestrial evidence was largely erased. Every Apollo sample, therefore, carries several possible origins at once: lunar crust or mantle, impactor material, solar particles, cosmic ray effects, and contamination introduced during collection or handling. Scientific progress depends on separating these signals. That separation became more powerful as instruments improved. When the first sample boxes arrived in Houston, scientists faced an unusual combination of abundance and scarcity. 382 kilograms is a large mass compared with most extraterrestrial sample returns. It is also tiny compared with a world whose surface area rivals that of a continent. Every gram had to be documented, protected, divided, and preserved. The samples entered cabinets and glove boxes filled with carefully controlled gas. Tools and containers were selected to minimize chemical contamination. Curators cataloged rocks, chips, fines, cores, and soils. Photographs linked pieces to their original specimens. Researchers requested small allocations for specific experiments, often receiving only fractions of a gram. Some analysis consumes material. A sample may need to be crushed, dissolved, heated, cut, polished, or exposed to a beam. The scientific value of an experiment must therefore be balanced against the permanent loss or alteration of part of the collection. Apollo planners understood that future instruments would be more capable than those of the early 1970s. They set aside material for later generations, including samples kept unopened or sealed under special conditions. That decision required restraint. Scientists of the Apollo era had urgent questions and a unique collection in front of them. Yet they accepted that some questions had not even been imagined and some measurements were not yet possible. The wisdom of this became clear repeatedly. Early laboratories could determine major minerals, bulk chemistry, and radiometric ages. Later methods examined isotopes at microscopic scales, mapped trace elements within individual crystals, counted atoms in tiny regions, and imaged internal structures without cutting a sample open. A piece of Apollo rock did not become scientifically exhausted after one study. It became a reference object revisited as technology changed. The Apollo Next Generation Sample Analysis Program made this principle visible. In 2019, researchers opened the upper portion of an Apollo 17 drive tube core designated 73002, the first newly opened Apollo sample in more than 2 decades. Its paired lower section, 73001, had been vacuum sealed on the Moon and remained unopened until 2022. The goal was not simply to repeat old work with newer machines. Scientists developed procedures to capture gases released as the container was opened, image the core before disturbing it, and preserve the order of fine layers. The program was timed so that researchers could refine methods for future lunar samples while studying material whose original field context was exceptionally well documented. The core came from a landslide deposit near the South Massif at the Apollo 17 site. It contained a vertical sequence of soil and small fragments. Each layer could record impact mixing, solar wind exposure, and volatile movement. The sample had waited almost 50 years for the right questions. This long delay also corrected a common misunderstanding about the Apollo collection. The rocks were not all analyzed once in the 1970s and then stored as museum objects. They remain working scientific material. New proposals are approved, tiny allocations are prepared, and results continue to alter models of the Moon. Radiometric dating lies at the center of that continuing work. Radioactive isotopes decay at known rates. By measuring parent isotopes and their daughter products in suitable minerals, scientists can estimate when a rock crystallized or when an event reset part of its isotopic system. Different isotope systems respond to different temperatures and processes, so agreement or disagreement among them can reveal a complicated history. A basalt may record the time lava cooled. An impact melt may record the time a collision melted and reset the rock. A zircon crystal may preserve an older age inside a younger breccia, because zircon is physically and chemically durable. Apollo samples gave absolute ages to lunar surfaces. Before them, crater counting provided only relative order. A surface with more craters was generally older than a nearby surface with fewer craters, but the number of years remained uncertain. Once a return sample could be tied to a mapped surface, its radiometric age anchored the crater count. Scientists then compared crater densities across the Moon and extended the relationship to other worlds. This is one of Apollo's most far-reaching achievements. Much of the chronology used for Mercury, Mars, and other solid bodies depends ultimately on the lunar record. Researchers adjust for differences in impact rates and dynamics, but the Moon provides the essential calibration between crater abundance and absolute time. A rock collected beside one lunar module, therefore, helps estimate the age of a plane on Mars that no human has touched. The method is powerful and imperfect. A sample may be ejecta from a distant crater rather than local bedrock. The landing sites are geographically clustered. Impact mixing can place old fragments on young surfaces and young material among old terrain. The calibration is strongest where sample context is secure and weaker when extrapolated far beyond it. Still, without Apollo, planetary surfaces would be dated much more loosely. The oldest lunar history is preserved especially well in zircon. Zircon crystals incorporate uranium when they form but reject much of the lead. Over time, uranium decays into lead, creating a robust clock. Some Apollo zircons formed more than 4.4 billion years ago, within the Moon's first 100 million years. These microscopic crystals show that crustal materials existed very early. They also record later heating, impacts, and metamorphism. A single grain can contain zones of different ages, like a geological manuscript written and partly revised. The age of the Moon itself is not defined by one rock. Formation was a process. A giant impact occurred. Debris accumulated. The Moon melted and differentiated. The magma ocean crystallized over time. Different isotopic systems may date different stages. Current estimates place lunar formation very early in solar system history, tens of millions of years after the first solid materials formed. The precise timing remains under study because models must distinguish impact age, core formation, magma ocean crystallization, and later resetting. Apollo did not return a label saying when the moon began. It returned clocks that scientists are still learning to read. The evidence also changed the origin story. In the mid-1970s, after researchers had studied the samples and geophysical data, scientists proposed a modern giant impact explanation. It remained controversial for years and gained broad support only after further modeling and a major reassessment of lunar origin theories in the mid-1980s. In this broad picture, a large protoplanet collided with the young Earth. Material from the impact entered orbit, formed a debris disk, and assembled into the moon. The hypothetical impactor is often called Theia, though that name refers to a modeled body, not an object whose separate remains have been identified. The impact idea explains several major observations. The Earth-Moon system has substantial angular momentum. The moon is depleted in metallic iron and has a small core. Many lunar materials are depleted in volatile elements relative to Earth. The moon experienced extensive early melting. A sufficiently energetic collision can connect these features. Apollo samples also showed striking isotopic similarities between Earth and Moon. Oxygen isotopes, and later measurements of several other elements, are extremely close. This indicates that the two bodies share closely related source material. At first glance, that may seem to make the giant impact obvious. Material thrown from Earth formed the moon. But the similarity also created one of the theory's hardest problems. Many early simulations produced a moon containing a large fraction of material from the impactor. If Theia formed in a different part of the solar system, its isotopic composition might be expected to differ measurably from Earth's, as meteorite groups and planetary materials often do. Why, then, are Earth and Moon so similar? Several possibilities remain. The impactor may have formed from material isotopically similar to Earth. The collision may have mixed and equilibrated vapor and melt more thoroughly than early models assumed. A high-energy impact may have placed a larger fraction of terrestrial mantle into the moon. Multiple impacts or different collision geometries may reproduce the observations. Modern simulations explore a wide range of energies, angles, spin states, and material behaviors. Some produce the moon rapidly. Others create a disk that evolves longer. No single scenario has closed every question. The giant impact is the leading framework because it explains the broad evidence better than capture, co-formation, or simple fission. It is not a finished film of an event that scientists can replay with certainty. Apollo made the origin of the moon more understandable and more demanding at the same time. The samples also revealed systematic depletion of many volatile elements. Zinc, for example, shows isotopic patterns consistent with high-temperature loss. Other elements tell more complicated stories. Water survived in some mantle sources. Chlorine isotopes suggest unusual volatile processing. The balance between loss, retention, and later delivery is still being reconstructed. The moon-forming event may have created a temporary atmosphere of silicate vapor and volatile gases. The hot young Earth may have shone in the lunar sky. Tidal forces were much stronger because the moon orbited far closer. The surface and interior evolved while impacts continued. None of this was visible to the Apollo crews. It emerged from chemistry measured long after the dust had settled in laboratories. Apollo samples also showed that the moon had differentiated. This means material separated by density and chemical affinity into layers. Metallic iron concentrated toward the center. Dense silicate minerals formed mantle. Buoyant plagioclase contributed to crust. Residual melts concentrated incompatible elements. Differentiation is a planetary process. It requires enough heat for large-scale melting and movement. The moon was not assembled as a permanently cold pile of debris. It became a world with internal structure. The Pharaohan anorthosites, including the class represented by the Genesis rock, were central evidence for the flotation crust. But the crust is not chemically simple. Other ancient rock suites, including magnesium-rich materials, suggest intrusions and mantle processes after primary crust formation. KREP records late-stage magma ocean residues. Basalts record partial melting much later. The textbook sequence of magma ocean, floating crust, and mare volcanism is a useful framework, but actual samples preserve overlapping processes. Impacts excavated deep rocks, mixed provinces, and reset clocks. Magma's intruded crust. Different mantle sources melted at different times. Apollo turned a smooth lunar timeline into a branching geological history. The mare basalts are especially important because they reveal thermal evolution. They formed over a wide interval, with major eruptions concentrated between roughly 4 and 3 billion years ago at the Apollo sites. Some lunar volcanism elsewhere continued later, as orbital crater counts and samples returned by robotic missions have shown. Apollo's equatorial near-side sites therefore captured only part of the volcanic record. Even within that limited region, basalts differed in titanium, trace elements, mineralogy, and age. High titanium basalts contain abundant ilmenite. Low titanium and very low titanium varieties came from different source regions and melting conditions. Chemical differences showed that the mantle had become heterogeneous during early differentiation. The basalts also contained vesicles in some cases, cavities formed by gas bubbles. In a world long considered dry, even small evidence of gas mattered. Volcanic glass beads provided stronger evidence for explosive release. Why did the moon remain volcanically active for so long after forming? Its small size should allow rapid cooling compared with Earth. Yet insulating crust, heat-producing elements, mantle composition, and local thermal anomalies allowed partial melting to continue. The near-side concentration of KREP and the thinner crust there may have helped magma reach the surface more easily. The Great Impact basins also influenced volcanism. Their formation excavated and fractured the crust, creating low regions and pathways. Later lavas filled many of these basins. The dark maria are therefore the combined products of impact and internal heat. First, a collision made a basin. Then lava flooded it. Later impacts cratered the lava. Regolith developed above it. Apollo astronauts landed on the final surface and collected pieces from several stages at once. This layering of causes is why the moon is not a simple record. The archive has been edited by impacts, but not erased. The returned rocks also showed that the moon cannot be divided neatly into only dark basalt and pale anorthosite. Those two families dominate the broad visual contrast, but small quantities of more evolved material occur within the collection. Some clasts are rich in silica and alkali elements. Others have compositions described with names such as granite, granophyre, quartz monzodiorite, or felsite. They are rare, often small, and commonly enclosed within breccias, yet they demonstrate that portions of lunar magma underwent extensive chemical evolution. As magma cools, early minerals remove certain elements while others remain in the melt. Repeated crystallization can produce residual liquids unlike the original mantle melt. On Earth, water, plate tectonics, crustal recycling, and long-lived magmatic systems contribute to the abundance of silica-rich continental rocks. The moon lacks those global processes, but local magmas could still differentiate enough to produce evolved compositions. The rarity of these rocks is part of the finding. The moon did not build continents like Earth's. It produced limited pockets of complex melt within a crust dominated by anorthosite, impact breccia, and basaltic products. Apollo samples therefore prevented an opposite pair of oversimplifications. The Moon was not geologically as diverse and continuously recycled as Earth, but neither was it chemically primitive in every place after its first crust formed. Glass told a similarly varied story. Some lunar glass formed in volcanic eruptions. Green and orange beads carried information from the mantle and volcanic gases. Other glass formed during impacts, when shock melted target rock or soil. Micrometeorites produced tiny glassy coatings and agglutinates. Larger collisions created melt sheets, droplets, and fragments that cooled at different rates. Two glass beads can look similar under ordinary light while recording entirely different events. Composition, texture, shape, inclusions, and geological context help distinguish them. Impact glass can sometimes be dated to the event that created it, but it can also be reheated or mixed. Volcanic glass may preserve mantle chemistry more directly than a crystallized basalt because rapid cooling freezes the melt before many minerals separate. Melt inclusions sealed inside crystals may protect volatile compounds that escaped from the surrounding magma. This is why laboratory analysis had to move beyond naming a rock by appearance. The scientific question became not only what material was present, but what process created it, when that process occurred, and what happened to the sample afterward. Even color required caution. Orange soil was volcanic glass. Green glass came from a different volcanic composition. Dark mare surfaces were basaltic, but also darkened by iron-bearing minerals and space weathering. Bright crater rays could indicate freshness rather than a different bedrock. Pale highland fragments often contained abundant plagioclase, yet a breccia's overall color could hide a mixture of clasts. The Moon's apparent monochrome landscape was chemically and texturally richer than the eye suggested. Apollo crews noticed subtle shades despite harsh lighting and colored visors. They used descriptive terms such as gray, tan, brown, white, green, and orange, but laboratory color standards and mineral measurements were needed to turn those impressions into reproducible evidence. The difference between seeing and measuring never made the field observation less important. Without Schmidt noticing an unexpected patch, the orange soil might not have been sampled with the same priority or context. Without the laboratory, its origin would have remained unknown. This partnership between recognition and analysis is the central method of Apollo geology. Apollo also helped establish the importance of impact melt. When a large body strikes at cosmic speed, pressure and temperature rise almost instantly. Rock can melt, vaporize, fracture, and flow. Melt pools cool into new rocks. Ejecta travels outward. Shock waves transform minerals. Before lunar exploration, many planetary landforms were interpreted too readily through terrestrial volcanism. Apollo 16's Highland surprise and the abundance of breccias showed that impacts can imitate or overwhelm other processes. Shock features in minerals became diagnostic. Planar deformation, high-pressure phases, glass, and melt textures helped identify terrestrial impact structures as well. Lunar geology strengthened the recognition that Earth's surface had also been shaped by collisions, even though erosion and tectonics concealed much of the evidence. Apollo science traveled back from the Moon into Earth geology. One sample may even preserve a fragment that originated on ancient Earth. A clast in Apollo 14 breccia 14,321 has been interpreted by some researchers as a terrestrial rock ejected by an impact more than 4 billion years ago, when the Moon was closer to Earth. Its mineral chemistry and formation conditions were argued to fit Earth better than the Moon. The interpretation is intriguing but not settled. Lunar processes may also explain the clast, and establishing an earthly origin for a tiny ancient fragment is extremely difficult. The possibility is worth considering because impacts exchange material between worlds. Rocks blasted from Mars have reached Earth as meteorites. Earth rocks could have reached the Moon, especially when the bodies were closer together. The lunar surface might preserve pieces of early Earth that Earth itself recycled. If confirmed, such a sample would make the Moon an archive in the most literal sense, a place holding pages torn from our planet's lost beginning. Even without that extraordinary possibility, lunar samples already provide indirect evidence about early Earth. The impact rate recorded on the Moon affected both worlds. The timing of lunar formation constrains Earth's accretion. The shared isotopic composition links their reservoirs. The Moon's tidal recession records the evolution of Earth's rotation and oceans. The two bodies have never had separate histories. Laser ranging makes that connection measurable every night. Observatories obtain a return signal. The Moon raises tides on Earth, friction in oceans, and the solid planet dissipates energy. Earth's rotation slows very gradually, while angular momentum is transferred to the Moon's orbit. The Moon moves outward. The present recession rate of about 3.8 centimeters per year cannot simply be projected backward as a constant value because ocean shapes, continental positions, water depth, and tidal resonances have changed. Geological records of ancient tides help reconstruct the long-term evolution. Still, the direction is clear. The Moon was once much closer. Earth's day was shorter. Tidal interactions were stronger. The reflectors left by Apollo 11, 14, and 15, together with Soviet robotic reflectors and newer targets, allow researchers to measure this relationship over decades. They also test whether Earth and Moon fall toward the Sun in exactly the way general relativity predicts, examine relativistic precession, and constrain possible changes in gravitational physics. The reflected signal is faint. A laser pulse spreads across hundreds of thousands of kilometers. Only a few photons may return to the detector. Precision emerges through repeated measurements, careful timing, and modeling of Earth's atmosphere, station position, lunar orientation, and orbital dynamics. The experiment is calm in appearance. Light leaves Earth, reaches an array on a silent plane, and returns. Yet the result connects lunar geology, ocean tides, Earth rotation, and fundamental physics. Apollo's longest-lived instrument requires no battery because geometry does the work. Its endurance contrasts with the powered surface stations. In 1977, after years of data, NASA ended routine operation of the Apollo seismic and other LSEP stations. Budget and program priorities contributed to the decision. The instruments fell silent, leaving an unmatched dataset from a small near-side network. For decades, researchers continued reprocessing those recordings. Digital restoration recovered data once stored on old tapes. New algorithms detected events and refined locations. Measurements designed for computers of the 1960s entered modern analyses. The Moon did not need to quake again for the old instruments to make a new discovery. The information was already present, waiting for a better way to read it. The samples and tapes share this quality. Apollo's scientific return is not fixed at the moment of collection. It grows when a new method asks an old object a more precise question. Not all Apollo discoveries came from a named rock or a sophisticated instrument. Some came from walking, falling, digging, driving, and trying to work. The Moon's gravity is about 1/6 of Earth's. The astronauts did not become weightless, but their bodies and equipment weighed much less. Mass remained unchanged, so a heavy tool still resisted acceleration even though it was easier to lift. This difference produced unfamiliar movement. Walking normally was inefficient. Crews developed loping and hopping gaits. A spacesuit's pressure made it resist bending, storing, and releasing energy. The life support backpack shifted the center of mass. A small obstruction could cause a slow, awkward fall. Most falls were not dangerous, but standing again required technique. The weak gravity allowed an astronaut to push upward with arms and knees, yet the stiff suit limited motion. Fieldwork plans had to account for the physical cost of bending, collecting, carrying, and documenting samples. This human movement became part of soil mechanics. Footprints, rover tracks, drill resistance, trench walls, and the behavior of thrown material all revealed properties of regolith. The surface could support the lunar module, but bearing strength varied. In some places a boot made a shallow impression. In softer crater rims or disturbed soil it sank more deeply. Rover wheels compressed and churned the upper layer while maintaining traction through wire mesh and chevron treads. The astronauts dug trenches and described changes below the immediate surface. Soil often became denser with depth. Clods could hold together temporarily even though the material was dry, because angular grains interlocked and electrostatic or cohesive forces acted at small scales. Core tubes were difficult to drive and retrieve. The resistance showed that the regolith had a structure built through billions of years of compaction and impact mixing. It was not an endless uniform layer of flour. The fear that a spacecraft might vanish into deep dust had been put to rest before Apollo, but the landings gave engineers direct measurements. The result mattered for every future foundation, wheel, drill, habitat, and landing pad. Apollo also revealed the danger of engine exhaust interacting with regolith. During descent, the lunar module's engine accelerated dust outward in a thin sheet. Without air to create a turbulent cloud, particles stayed close to the ground and traveled rapidly. Visibility decreased near touchdown as surface features disappeared beneath moving dust. The plume excavated only a modest depression beneath the engine, but it transported grains and could sandblast nearby equipment. Apollo 12's retrieved surveyor hardware showed that particles from Intrepid's landing had reached and affected the robot despite its position below the surrounding terrain. Future lunar vehicles may be larger and more powerful. Apollo therefore found a problem that extends beyond its own era. Landing one spacecraft can threaten instruments, habitats, or historic sites some distance away. The airless surface also changed how distances and shapes appeared. On Earth, atmosphere gives depth cues. Distant objects become bluer, dimmer, and less distinct. The horizon is softened by haze. On the Moon, a far mountain can look sharp enough to touch. Without trees, buildings, or familiar objects, scale becomes ambiguous. This contributed to Apollo 14's difficulty locating Cone Crater and affected navigation on other missions. A boulder might be larger and farther away than expected. A slope that looked gentle could demand more effort. Sunlight created stark illumination, while shadowed areas could lose visible detail. The sky remained black even during lunar daytime because there was no atmosphere to scatter sunlight. Stars were usually difficult to see from the bright surface because the astronauts' eyes and cameras were adapted to illuminated terrain, not because stars were absent. The horizon was closer than on Earth because the Moon is smaller. From a standing position on a relatively level plane, local terrain curved away within a few kilometers. Mountains and crater rims extended the view, but the sense of standing on a small spherical world was physically present. Earth hung in the sky at a nearly fixed location for each landing site, shifting slowly through lunar libration. It showed changing phases opposite those seen from the Moon on Earth. To the astronauts, it was not merely a beautiful object. It was the source of radio signals, navigation, tides, and every living thing they knew. The Moon itself offered no weather. No wind moved the flag after the astronauts stopped handling its support. No rain softened tracks. No sound traveled through the vacuum between astronaut and landscape. Inside a suit, however, the Moon was not silent. Astronauts heard pumps, fans, radio voices, breathing, and vibrations conducted through their bodies and equipment. A hammer strike could travel through a tool and suit. The absence of atmospheric sound did not create an absence of experience. Temperature was another difference between simple description and reality. The lunar surface reaches extremes during its long day and night, but the astronauts landed during local morning, when illumination was useful and thermal conditions manageable. Their suits controlled body temperature, while white outer layers reflected sunlight. A sunlit rock and a shadowed surface could have very different temperatures. Instruments exposed for years had to survive repeated cycles far beyond the duration of a human visit. Apollo found no substantial atmosphere, but the moon is not surrounded by perfect emptiness. It possesses an extremely tenuous exosphere, with atoms and molecules so sparse that they rarely collide. Some particles come from solar wind, radioactive decay, micrometeorite impacts, or release from the surface. Apollo instruments detected aspects of this environment, though spacecraft exhaust and other contamination complicated measurements. This distinction matters. Saying the moon has no atmosphere is useful in ordinary speech. Scientifically, it has a boundary environment where particles are created, move in ballistic paths, escape, or become trapped. Apollo astronauts temporarily altered that environment. Lunar module engines released gases. Suits vented. Equipment outgassed. The presence of humans created a local artificial atmosphere so thin and transient that it would be meaningless on Earth, yet measurable against the moon's natural background. Exploration leaves traces even when footprints appear unchanged. Apollo also carried biological uncertainty. Before the first samples returned, no one could prove that the moon was sterile. The probability of lunar organisms seemed low, but the consequences of introducing an unknown hazard to Earth demanded caution. Apollo 11, 12, and 14 crews entered quarantine after splashdown. Samples were handled in the Lunar Receiving Laboratory under containment procedures. Animals, plants, and microbial cultures were exposed to lunar material in tests. No evidence of lunar life or infectious hazard appeared. Later missions ended the quarantine requirement. The absence was scientifically meaningful, though it was not surprising. The equatorial surface offered no liquid water, stable atmosphere, organic-rich environment, or protection from radiation. Samples contained carbon compounds and other materials that required careful separation from terrestrial contamination and meteoritic input, but nothing demonstrated biology. Apollo found a moon inhospitable to life as we know it. It did not prove that every lunar environment is chemically simple. Permanently shadowed polar regions were not visited. Their extreme cold can trap water ice and other volatiles delivered by impacts or produced through surface processes. Later robotic missions provided evidence for these deposits. This creates an important separation between what Apollo found and what the moon contains. The Apollo sites were all on the near side at relatively low latitudes. The crews landed in sunlight. Their samples represented mare plains, highlands, basin ejecta, volcanic deposits, and regolith from those regions. They did not sample the deep cold traps near the poles. Early statements that the moon was completely dry came partly from real measurements and partly from geographic limitation, contamination concerns, and instruments unable to detect very small amounts of indigenous water. When polar ice was suggested by later missions, it did not mean Apollo had failed. It meant the first 6 landing sites did not contain every lunar environment. The same is true of geology. Apollo found ancient volcanism at all relevant sites, but it could not date every lava plain. It found impact melt ages, but not samples from every major basin. It found a magnetic history, but only fragments of the dynamo record. It found moonquakes, but its network covered only part of one hemisphere. A world cannot be fully represented by 6 places. Still, the places were chosen intelligently within engineering limits. Each mission expanded the range of terrain and capability. The sequence itself became a scientific strategy. Apollo 11 sampled a mare and proved safe return. Apollo 12 repeated mare sampling in a different region, reached a robotic target, and established a long-lived instrument station. Apollo 14 reached base in Ejecta and collected impact breccias at Framaro. Apollo 15 combined mare, mountain front, rill, rover, deep core, and heat flow. Apollo 16 tested the highlands and overturned a volcanic interpretation. Apollo 17 brought a geologist to a valley containing highland massifs, volcanic deposits, boulders, and complex ejecta. The pattern moved from operational survival toward comparative planetary geology. Training evolved with it. Early astronauts received geology instruction, but later crews spent much more time in terrestrial field sites. They learned to describe color, grain size, texture, layering, contacts, and orientation. Geologists in mission control followed their words, photographs, and television images. The communication loop was unusual. The person holding the rock stood on the moon. Specialists listening on Earth could ask questions or change priorities. Time delay was only a little over a second each way, short enough for conversation, but long enough to shape rhythm. The astronaut had limited vision and time, but direct physical context. The scientists had broader expertise in maps, but no direct view beyond cameras. Good fieldwork depended on combining them. Sample bags carried numbers. Photographs showed the ground before and after collection. A gnomon provided scale, orientation, and color reference. Voice transcripts recorded observations. Maps reconstructed traverses. Occasionally, documentation was incomplete. A sample might be collected quickly or placed in a bag with several fragments. Dust obscured labels. Cameras malfunctioned. Human memory had limits. Yet the overall context of Apollo samples remains exceptional. Each rock belongs to a documented expedition rather than an unknown meteorite fall. Lunar meteorites are invaluable because they probably come from many regions, including the far side. But their exact source craters are usually unknown. Weathering on Earth can alter them. Apollo rocks arrived with location, photographs, and nearby samples. This difference resembles finding a page with no book title compared with finding the same page still inside its chapter. Apollo orbital crews added another layer of context. While two astronauts worked on the surface, the command module pilot orbited alone. Cameras photographed broad regions. Spectrometers mapped chemical elements. Radar and laser altimeters measured topography. Particles and fields were studied above the moon. Apollo 15 and 16 released small subsatellites to measure magnetic and particle environments. Apollo 17 carried instruments in the Scientific Instrument Module Bay, including radar sounding and mapping experiments. The command module pilot performed a spacewalk during the return journey to retrieve film canisters from outside the spacecraft. Orbital data connected narrow traverses to regional geology. A sample's chemistry could be compared with remote sensing of surrounding terrain. Conversely, the known composition of return material helped interpret orbital spectra elsewhere. This calibration continues. Laboratories measure exactly how Apollo minerals and soils reflect light across many wavelengths. Orbital instruments observe similar spectral features across the moon. Return samples turn color and absorption bands into mineral maps. The process is not automatic. Grain size, space weathering, illumination, glass content, and mixtures can change spectra. A highland surface may contain fragments from several rock types, but ground truth allows increasingly reliable interpretation. Apollo therefore taught scientists how to read the moon from orbit long after the astronauts left. The mission photographs also became new data decades later. Modern image processing, digital scanning, In comparison with lunar reconnaissance orbiter images, improved maps of landing sites and traverses, tracks, equipment, descent stages, and disturbed soil became visible from orbit at high resolution. These images confirmed locations and allowed researchers to examine how astronaut activity changed surface reflectance and thermal properties. The landing sites became experiments in the long-term preservation of human disturbance. Footprints do not last because the moon is perfectly unchanging. Micrometeorites will slowly erode them. New impacts will eventually overturn the soil. But without weather, the process may take extremely long periods. The tracks are temporary on geological timescales and enduring on human ones. Apollo samples recorded cosmic rays as well. High-energy particles traveling through space create damaged tracks and produce new isotopes in exposed minerals. By measuring these effects, researchers estimate how long a rock or grain remained near the surface. A boulder excavated recently by an impact may have a short exposure age even if the rock itself crystallized billions of years ago. Crystallization age and exposure age answer different questions. This distinction helps reconstruct movement. A rock may form deep in a lava flow, be excavated by a crater, rest on the surface, be buried by ejecta, and later be exposed again. Different clocks preserve pieces of that journey. The lunar surface is still, but the material within it has biographies. Tiny glass spherules record impact or volcanism. Agglutinates record micrometeorite melting. Solar gases record exposure. Cosmogenic isotopes record radiation. Mineral ages record crystallization or shock. Magnetic remnants records vanished fields. Soil layering records burial. The astronauts collected objects small enough to fit into bags, but those objects contain processes extending from the core of the moon to the surface of the sun. This is why the phrase moon rock is almost misleading. A sample is not merely matter from a location. It is a set of clocks and memories. Apollo also found that some apparently ordinary samples were extraordinary in purity or preservation. Troctolite 76,535, collected by Apollo 17, is a coarse-grained rock containing olivine and plagioclase. It has been studied as a relatively pristine deep-seated sample, useful for understanding crust and mantle processes. Because it cooled slowly, its minerals grew large. Its textures and isotopes preserve information about magma beneath the surface. Other samples called pristine still experience some history, but they escaped the intense brecciation common in many highland rocks. Finding such material among impact-shattered terrain was scientifically valuable. It allowed researchers to study internal magmatic processes without every signal being dominated by shock. At the other extreme, regolith breccias preserve ancient soil compacted into rock. Some trap grains and solar wind components from surfaces that no longer exist. They can act as paleoregolith samples, recording the space environment of an earlier era before burial. A buried ancient soil layer could preserve information about the young sun, galactic cosmic rays, and nearby supernovae. Apollo samples hint at this possibility, while future drilling between dated lava flows may provide cleaner archives. Once again, a discovery made from returned material creates a more precise question for the next expedition. Apollo's success also changed how sample return is valued. Instruments carried to another world must be designed years before launch. They answer questions anticipated at that time and operate within strict limits of mass, power, calibration, and environment. A returned sample can be studied by an entire planet's laboratories. It can be examined by instruments invented decades later. Results can be repeated independently. A portion can be preserved for the future. This does not make robotic science inferior. Robots can reach places humans cannot, remain for years, and make measurements without life support demands. Robotic sample return missions have delivered material from asteroids, comets, the solar wind, and the moon. The strongest exploration programs combine orbital mapping, robotic scouting, in situ instruments, and carefully selected returns. Apollo demonstrated the unique power of bringing documented planetary material to Earth at large scale. Its sample mass remains unmatched for another world. More important, its diversity includes rocks, soils, cores, glasses, breccias, basalts, anorthosites, and hardware exposed on the surface. The collection is not a single answer. It is an ecosystem of evidence. There were also things the astronauts expected and did not find. They did not find thick dust swallowing the landers. They did not find current rivers, seas, weather, or wind. They did not find a global magnetic field. They did not find obvious active volcanoes. They did not find biological material native to the moon. They did not find a simple, undisturbed primordial crust. Impacts had broken and mixed it extensively. They did not find one uniform lunar composition. They did not find a world that could be described accurately as merely cold, dry, and dead. The negative results narrowed possibilities. The positive surprises opened new ones. Even the apparent dryness changed form. The sunlit equatorial surface is extraordinarily arid. Liquid water is unstable there. Most Apollo minerals are depleted in hydrous alteration compared with Earth. But hydrogen exists in volcanic glass. Hydroxyl can form or move near the surface, and polar cold traps preserve ice. The correct picture is not a wet moon or a dry moon. It is a moon where water exists in small, unevenly distributed reservoirs with different origins and histories. Some water was present in the mantle. Some may be delivered by asteroids or comets. Some hydrogen arrives in the solar wind and reacts with oxygen in minerals. Some molecules migrate and become trapped in permanent shadow. Impacts can release or destroy deposits. Apollo found the first pieces of this complicated cycle without knowing the full pattern. The same can be said of carbon, nitrogen, sulfur, and noble gases. Volatile elements are scarce, mobile, and vulnerable to contamination, but not absent. Future science depends on preserving them carefully. That is why the vacuum-sealed Apollo 17 core opened in 2022 mattered. Researchers wanted to capture gases before they escaped into laboratory air. Procedures developed around an old sample became rehearsal for new ones. The Apollo collection keeps teaching not only lunar history, but how to conduct lunar science. The scientific importance of Apollo becomes clearest when the discoveries are placed back into the history of Earth. Earth and Moon formed in the same region of the young solar system and have remained gravitational partners for almost their entire existence. Large impactors that crossed lunar orbit could also cross Earth's. Solar radiation reached both worlds. Material ejected from one could sometimes reach the other. Yet Earth's earliest record is fragmentary. Very old zircon crystals survive, and a few ancient rocks remain. But most crust from the first 500 million years has been transformed or destroyed. The Moon preserves extensive terrain from that interval. Its highlands, impact basins, and ancient samples allow scientists to investigate an era that Earth has largely erased. The lunar impact record constrains the environment in which early Earth cooled, formed oceans, and developed conditions for life. If giant impacts were frequent, they could vaporize oceans locally or globally, alter atmospheres, and create hydrothermal systems. They could destroy habitats and create new ones. The exact relationship between bombardment and life is not simple. Early impacts were not necessarily global sterilizers. Microbial life, if present, might survive underground or around hydrothermal environments. Impact heating could be devastating in one region and chemically productive in another. Apollo did not determine when life began on Earth. It provided part of the astronomical and geological setting in which that question must be asked. The lunar magma ocean also offers a comparison with the early stages of rocky planets. Large bodies accumulate heat and differentiate. Crust forms, overturns, melts, and is bombarded. By understanding the Moon's relatively accessible record, researchers test processes that operated on Mercury, Mars, Earth, and worlds around other stars. The Moon is small enough to have cooled substantially, yet large enough to preserve a complex interior. It occupies a useful middle ground between asteroids and planets. Apollo samples also show that the distinction between planetary formation and later geology can be blurred. The final stages of accretion involved giant impacts. Those impacts produced melting and differentiation. Later basin-forming collisions rearranged the crust. Volcanism filled the scars. Smaller impacts created regolith above the lava. The surface where Apollo landed was the result of all these stages. At Tranquility Base, Armstrong and Aldrin stood on basalt formed billions of years after the Moon's initial crust began to crystallize. Yet their soil contained fragments and glasses from later impacts and exposure to the modern solar wind. At the Ocean of Storms, Conrad and Bean sampled a different volcanic source and visited a machine altered by years on the lunar surface. At Fromaro, Shepard and Mitchell walked across debris from a basin-forming collision and approached a crater that had excavated the debris again. At Hadley Apennine, Scott and Irwin moved between mare, mountain, rill, ancient crustal fragments, volcanic glass, and a deep soil sequence. At Descartes, Young and Duke discovered that apparently volcanic highlands were dominated by impact products. At Taurus Littrove, Cernan and Schmidt found explosive volcanic beads beneath gray soil, sampled mountain material, and explored a valley shaped by basin history, volcanism, landslides, and impacts. These were not 6 repetitions of one landing. They were 6 chapters selected to test and revise a developing model. The revision did not stop in 1972. The dry Moon became a world with small but meaningful reservoirs of internal water and with ice preserved in polar cold traps. The inactive Moon became a world with quakes, young faults, residual heat, and a complicated thermal history. The non-magnetic Moon became a world that had once generated a dynamo. The neat picture of one brief late cataclysm became a debate about impact flux, sampling bias, basin ages, and the overwhelming influence of Imbrium ejecta across the Apollo collection. None of these changes made Apollo less important. They showed what happens when preserved evidence outlives the first generation of instruments used to study it. A sample once described as dry may contain hydrogen below the detection limit of an earlier machine. An age once treated as a global marker may belong mainly to one basin whose debris reached several landing sites. A crustal thickness inferred from a small near-side seismic network may be revised when a later spacecraft maps gravity across the whole Moon. The evidence remains, while the questions become more precise. This is why Apollo science did not end when the last ascent stage left Taurus Littrove. Schmidt discovered orange soil because he recognized an unexpected color in the field. Laboratories discovered that the color came from volcanic glass, that the droplets formed in ancient fire fountains, and that volatile elements traveled with the eruption. Decades later, instruments sensitive to microscopic hydrogen gradients showed that water had once been dissolved in the magma. Scott and Irwin recognized paleonorthosite at Spur Crater. Laboratory measurements placed it within the story of the ancient crust. Comparisons with other samples and later orbital mapping strengthened the idea that the young Moon had possessed a vast magma ocean from which buoyant plagioclase rose. Armstrong and Aldrin discovered that the surface would support a lander and preserve a footprint. Microscopes revealed angular grains, impact glass, agglutinates, and metallic particles produced by space weathering. What felt like dust beneath a boot became a record of billions of years of bombardment and direct exposure to space. The astronauts were the field end of an experiment that continued across generations. That experiment also revealed the limits of 6 successful landings. Every Apollo site lies on the near side, at low or middle latitude, within a comparatively restricted portion of the Moon. The collection is large by extraterrestrial standards, but geographically narrow. The far side, the polar regions, the youngest volcanic terrains, and the deepest basin on the Moon remain beyond the direct reach of Apollo geology. The South Pole Aitken Basin is one of the most important missing chapters. It is enormous, ancient, and excavated material from deep within the Moon. A return sample tied securely to its formation could transform the chronology of early bombardment and test whether familiar age clusters really represent a system-wide event or mainly the repeated sampling of near-side basin debris. The far side presents another unanswered question. Its crust is generally thicker, its volcanic plains are far less extensive, and it lacks the broad concentration of KREP-rich terrain seen on the near side. Apollo samples helped reveal the chemical ingredients of the near-side provinces, but they cannot by themselves explain why the two hemispheres evolved so differently. The poles contain another kind of archive. Permanently shadowed craters can remain cold enough to preserve ice and other volatile compounds for immense periods. Those deposits may include material delivered by asteroids and comets, hydrogen implanted by the solar wind, molecules released from the interior, and substances moved across the surface before becoming trapped in darkness. Apollo never entered those cold regions. Its equatorial samples taught scientists how easily volatile evidence can be lost, contaminated, or overlooked. Future polar samples will require containers and procedures designed to preserve gases and ice from the moment of collection. The interior also remains only partly known. The Apollo seismometers prove that the Moon has a crust, mantle, and small core, but the network occupied one limited part of the near side. A wider array could listen to quakes from many directions, trace waves through the core more clearly, and reveal how internal structure varies across the globe. The same geographic problem affects heat flow. Apollo measured it successfully at only 2 sites, both within a geochemically unusual near-side region. New measurements far from KREP-rich terrain could show how unevenly radioactive elements and residual heat are distributed. The ancient magnetic field remains difficult to reconstruct. Some rocks record strong fields, while others preserve weaker or more ambiguous signals. More samples with secure ages and well-understood cooling histories could show when the dynamo began, how long it lasted, and whether it weakened smoothly or returned in separate episodes. Each unanswered question grows directly from something Apollo found. Future crews and robots will therefore not repeat Apollo. They will extend its method into landscapes Apollo never reached. Near the South Pole, sunlight can skim the horizon while nearby crater floors remain in permanent darkness. Temperatures, visibility, terrain, communication, and dust behavior will differ from the conditions at the 6 equatorial landing sites. A rover may investigate a shadowed region before a person enters it. Orbital instruments may map hydrogen and minerals. Astronauts may then recognize relationships, select samples, and change a plan when the ground contradicts the map. Apollo showed why that chain is powerful. It also showed that exploration can alter the evidence. Thruster plumes accelerate dust. Exhaust introduces gases. Foot traffic changes the optical and thermal properties of soil. Drilling heats and mixes material. Vehicles, tools, habitats, and spacesuits carry substances that do not belong to the original environment. At a polar volatile deposit, careless activity could disturb the very molecules an expedition was sent to study. Future explorers will need clean tools, sealed containers, carefully planned approach routes, control samples, and an exact record of what each spacecraft released. The Moon's lack of wind does not make contamination disappear. It allows particles and gases to follow different, often more predictable paths. Historic Apollo sites require similar care. The descent stages, instruments, tracks, and disturbed soil form a thin human layer above billions of years of natural geology. Materials left there have experienced vacuum, radiation, dust, and extreme temperature cycles for more than half a century. They are cultural remains, engineering experiments, and scientific reference sites at the same time. Surveyor 3 gave Apollo 12 an early chance to examine hardware after a few years on the Moon. Future studies may eventually reveal how equipment changes over much longer intervals, but only if the first landing sites are protected from unnecessary disturbance. Apollo also established the chemistry behind possible lunar resources. Oxygen is bound within minerals. Solar wind gases are implanted in parts of the regolith. Polar ice may support crews or provide raw material for oxygen and hydrogen. Basalt and anorthosite could become construction material. But a substance detected in a laboratory is not automatically an accessible resource. Extraction requires power, machinery, maintenance, transport, and a reason to use the product. Apollo did not reveal effortless treasure. It revealed a world whose materials might become useful only through careful engineering. The most valuable return was knowledge. The samples established that the dark plains are ancient lava flows, and that the bright highlands include remnants of a plagioclase-rich primary crust. They showed that the young Moon was extensively molten, differentiated into internal layers, and later produced magmas from chemically different parts of its mantle. They showed that impacts did more than make craters. Impacts shattered, melted, buried, transported, and recombined the crust until breccias became one of the Moon's defining rock types. The instruments added a second dimension. Seismometers found quakes and a layered interior. Heat flow probes detected energy still escaping from within. Magnetometers and remnant fields in rocks revealed a vanished dynamo. Solar wind foils collected atoms from the sun. Laser reflectors began a measurement of the Earth-Moon relationship that continues long after the powered stations fell silent. The collection then changed the history of two worlds. Radiometric ages anchored the chronology of lunar surfaces and became the foundation for estimating ages across much of the solid solar system. Ancient crustal fragments preserved an era largely erased on Earth. Impact melts constrained the environment in which the young Earth cooled, and the earliest habitats may have formed. Isotopes tied the Moon closely to Earth, while forcing every origin theory to explain both their similarity and their structural differences. In the mid-1970s, scientists proposed a modern giant impact explanation in which a large protoplanet struck the young Earth and produced orbiting debris. The idea remained controversial for years. Only after further modeling and a major reassessment of lunar origin theories in the mid-1980s did it gain broad support. It is now the leading framework, but Apollo continues to make it more demanding rather than complete. The Moon's close isotopic relationship with Earth, its small iron core, its volatile depletion, its surviving water, and its early melting all have to emerge from one physical history. Different impact energies, angles, spin states, and degrees of mixing produce different results. Apollo supplied the constraints that every successful model must satisfy. This is the deeper pattern of the program. A basalt recorded mantle melting and lava spreading across an impact basin. An anorthosite recorded minerals rising through a magma ocean. A breccia recorded older rocks shattered and reunited by collision. A glass bead recorded gas escaping from a volcanic fountain. A magnetic grain recorded a field that no longer surrounds the Moon. A soil particle recorded atoms arriving from the sun. A zircon recorded time from the first age of the Earth-Moon system. A seismic trace recorded a crack responding to Earth's tides. A reflected photon recorded the slow widening of the lunar orbit. The astronauts carried objects small enough to fit into bags, but those objects connected the lunar core, the young Earth, the early solar system, the sun, and the space between worlds. The final departure from Taurus Littrov took place on December 14, 1972. Gene Cernan climbed the ladder after expressing hope that people would return with peace and hope for all humanity. The ascent stage rose above the valley, leaving the descent stage, rover, instruments, tools, tracks, and disturbed dust behind. The valley became quiet again. There was no wind to soften the wheel marks. No rain entered the sample trenches. Orange glass remained beneath gray soil near Shorty Crater. Boulders rested at the bases of the massifs. Seismometers listened for several more years. Reflectors waited for laser pulses from Earth. The samples traveled in the opposite direction. They entered laboratories, were photographed, cataloged, divided, measured, and preserved. Small portions went to researchers around the world. Some were consumed during analysis. Others remained sealed for questions and instruments that did not yet exist. More than half a century later, that decision continues to matter. A core opened after decades can release gases preserved since collection. A zircon can refine the timing of an ancient event. A glass bead can constrain the water content of the mantle. A magnetic crystal can challenge a dynamo model. An old seismic recording can reveal an event missed by earlier processing. A laser pulse can still return from an array placed during the first landing. The footprints are the most visible legacy, but the evidence is the deeper one. Apollo found that the moon was not a blank stone suspended beside Earth. It was a world formed by heat, separation, eruption, collision, fracture, radiation, and time. It had once been molten. It had built a crust, generated a magnetic field, released volcanic gases, and continued to move quietly beneath an apparently motionless surface. It was closely related to Earth and profoundly unlike it. Apollo went to the moon expecting to collect rocks. It returned part of the early history of two worlds. And beneath the gray dust, under a black sky, the astronauts found that the nearest world beyond Earth was not empty at all. It was full of evidence. Good night.